Hello everyone. I think your evening or morning or whatever, it's good. So we can start. So I hope you all are doing well. So I'm Vinod Kumar and I'm from India. So currently I'm an assistant manager, Reservoir, in the leading operating company in India. So welcome to this course on production optimization using nodal analysis. It's a very first webinar that we are providing to let you understand the crust of this course and give you detailed insight so that we can take this course forward with your support in the future. So we are extremely happy and excited to have you here. I am basically a master's grad from in petroleum engineering from a institute in India, and I'm working since the very first of my career as a reservoir engineer. So during this course, we will be sharing practical insights and techniques to help us better manage production operations. We really appreciate your efforts to take out your time. We will make every effort to make this informative for you and we'll give you as much information as possible. If you have any query, you can ask me anytime and or else you can put in the chat box. So we'll be addressing it later at the end. That's all from my side. So let's start our webinar. So let's discuss the facts first. So can anyone answer me what is optimization? If you can just unmute or you can type the chat box. What do you understand about optimization from your experiences as a student or as a professional? You can type in the chat box if you're unable to answer verbally.
بلاني مهتمة الأمر على حقد معودة بالشمس شمسي ولا رمتي قاعدة تاكل
Okay, I got an answer. Oh, sorry. So optimization is something very different from maximization. So optimization is having or getting something in an optimum manner. So since we are talking about production optimization, we are supposed to optimize our production. It means not a maximum or not a minimum. We should be somewhere in between the maximum and minimum. We need to have as optimum production as possible. It may not be at the maximum and it should not be the minimum. So that is optimization, especially in the terms of production optimization, like optimizing production to the maximum level that is possible. So in this particular webinar, we'll be discussing on well performance and system analysis, which is production system and reservoir fluids and their relevance for our study on production optimization. And we will also understand how do we get hydrocarbons to surface from tubing performance and tubing size selection through nodal analysis. And we'll do ultimate system analysis using nodal analysis. Okay. So what are the basic fundamentals of production optimization as a different course in petroleum engineering or the oil and gas industry? So to know that, we need to first understand the components of inflow performance, the components of vertical lift performance, and the combination of these both together. So as I have told you before, production optimization is the balance between production rate or deliverability and of course demand. So if you can see the figure of the entire well, subsurface to surface integration here, you can see the reservoir which has a lot of, there's a uh, gradient in the reservoir, which is the pressure difference between the reservoir end or the boundary to the well. So you can see in this particular reservoir, there's gas cooling happening and there's loss of gas with drawdown. So generally what happens is, if it is a conventional oil reservoir, if the pressure is more than bubble point pressure, to clear your doubt, bubble point pressure is the pressure below which first gas bubble comes out from oil. So if it is an undersaturated reservoir and if the pressure is above PB, then you expect you expect oil, single phase oil at the downhole. But from the bottom hole to the surface till it reaches the wellhead, there is some gas separation happening in the tubing. If there's a single tubing completion, that happens. So, that is where the production engineer generally takes a second turn to understand how he can optimize production. Because if it's a lot of gas that is coming out, and if the crude is having high GOR, the gas oil ratio, it's very tough to optimize production. So that is the time then when we use nodal analysis to balance between the production rate and the actual well deliverability. And this all depends on the demand that is required from that field. So production optimization includes a good understanding of production systems and reservoir fluid. So the system includes reservoir, which is generally from IPR, the inflow performance relationship, then wellbore, which includes completions and tubing, and surface facilities, the flow line separators, pipelines, etc. So integration or the combination of these both will be taken forward through nodal analysis. So production systems can be very simple to very complex. Simple, I mean a simple reservoir, common completion, three casing policy, two casing policy, four casing policy with a single tubing and good and integrated surface facilities. But complex when we have an SRP, which is an artificial lift mechanism, and when we are injecting water, and if there are multiple wells or there are multiple completion, multi-zone completion, commingled production. Okay, so we need to also take that into consideration. Movement of transport of reservoir fluid from reservoir to alleged surface requires energy, which is generally given by the reservoir pressure. If it is a natural energy mechanism, or if there is an artificial lift, the reservoir generally delivers the fluid from this. Let me just write something. Yeah, from the reservoir to the bottom hole with its natural energy. So if you can see the pressure profile, it will be something like this, the pressure drop. But from bottom hole, you need to bring the entire fluid to the surface. If there is not enough energy at the bottom hole, we need to go for artificial lift. Even that can be understood by nodal analysis during production optimization. The pressure drop of the fluid at any time would be the initial fluid pressure minus the final fluid pressure. So if I take the delta P from reservoir till separator, it is P R bar minus P separator, which is generally the initial pressure of the system. So now let us understand what is reservoir fluid. So to understand that, we need to deeply go into the phase behavior, whether it is a dry gas or wet gas or condensate or simply oil like black oil, near critical oil, volatile oil, or even water. So also, we need to understand fluid properties from gas and liquid. So these all will be the actual components of the course that we carry forward in the future. Because this is an introductory webinar, I'm not going deep into this. My main focus today would be on the production optimization part. So these all background will be given to you in the actual course. And also laboratory measurements to understand the fluid properties from constant composition expansion tests and CVD, constant volume depletion, and DLE, differential liberation equilibrium experiments. So these all will be taught to you in the future. So properties of reservoir fluid like FEF, the formation volume factor, which includes BO and BG for oil and gas, the produced gas oil ratio, which is RP, and even RS, solution gas oil ratio, compressibilities of oil and gas and even water, bubble point pressure, gas and oil gravities and densities and viscosities. So these all come from the laboratory analysis, from PVT analysis. So this, which will be the actual component of the course that we go ahead in the future. So also fluid phase behavior, we can classify the fluid into three basic types: single phase, two phase, or a combination. So this information is very essential for IPR equation to be generated or to be applied to the optimization procedure. So from the phase diagram, we will understand the actual pressure decline from the reservoir till surface. If I talk about the condensate reservoirs, so it will be somewhere here if it is near critical gas condensate, or if it is retrograde condensate, it will be somewhere here, the drop line. So since the pressure is more than dew point pressure, this curve is the dew point curve, this curve. So this is the dew point pressure. The maximum pressure is the dew point pressure. So if the reservoir pressure is more than this, it is a single phase gas. But if it is less than this, the condensate starts coming in. So we'll always define three pressure decline points. One is the initial reservoir pressure condition, which is single phase gas. One is on the dew point pressure line, which is when the condensate starts falling down, which makes the gas more rich. And then the two phase envelope, the separator condition, if we extend it till this point, where a separator condition exists at a very low pressure and a certain temperature. Also, from the fluid phase behavior, we will extend that to rock properties, reservoir character, fluid qualities, flow paths, effect of delta P and back pressure, because the separator till the surface facility, we have a lot of back pressure on the fluid that is flowing. Fluid behavior in approach or entry to the wellbore, lift type and optimization of flow from bottom hole through tubing, operations effect on the flow rate, choke setting, because the optimization procedure is through choke setting. We will have a lot of restrictions or the bottlenecks, then separator operation, pipeline design, and startup or shutdown operations for stabilizing. So now the actual course started. Integration of all of this through system analysis. So IPR is defined as the functional relationship between the production rate and the bottom hole flowing pressure. PI is that which relates the production rate and the delta P. And PR is the ratio of actual productivity index to the ideal productivity index, where skin is 0, which is ideal. So the joining point between outflow VLP and the inflow IPR is the nodal point. If we talk about the bottom hole node, and the joining point between out wellhead to the in tubing will be the surface node or the wellhead node, and there is something else between the choke and the wellhead, which is a choke node. So we define three general nodes. One is bottom hole node, wellhead node, and the choke node in nodal analysis. So IPR, as I've told you, delta P is PR minus PWF from the reservoir to the bottom hole. Then PI will be J, which is Q by delta P, where Q is the flow rate of the fluid or even the gas, and delta P is the pressure drawdown. Generally in gas, we go for P square approach, which I'll be actually dealing in the future course of time. So this, if we plot between bottom hole flowing pressure and the flow rate, which this curve is a declining curve, which is having an exponential pattern. So this IPR curve is generally not linear if there is two-phase envelope. It should be linear up to the bubble point pressure, because that is when the single phase only comes in. And then it will take a curvature. So this is the bubble point pressure, PB. So after this, there is a two-phase envelope. Generally, it has to go till here, but it won't, because this Q is the liquid flow rate, QL. Since gas starts coming in below this PB, when P reservoir is less than PB, and also PWF is less than PB, gas starts coming in, this will tend to decrease the liquid flow rate and will try to increase the gas flow rate. That is why we have a reduction in the actual AOF. So whenever your PWF is 0, technically your Q is equal to J times P bar or P reservoir minus P bottom hole flowing. Whenever this is 0, it is simply Q is equal to J into PR. This means it is absolute open flow when the surface is open to atmosphere. So if you see the AOF at this point, at this two-phase regime, it is less, but AOF at single phase is more. So this window will be the gas that is producing at surface. So the second is TPR, tubing performance relationship, which is the term used to describe outflow performance. It is also called as VLP, vertical lift performance. So TP looks at optimizing or minimizing the pressure losses at lowest life cycle cost. By minimizing pressure drop, we can maximize production. So what is the pressure drop? Delta P, right? From bottom hole flowing to wellhead flowing, PHF. So this drop in pressure is delta P now in tubing. So if we can minimize this, we can maximize production. So this is the well completion for as an example. So as the flow passes through the pipe, the pressure inside changes. These changes can be described by three components. One is gravity force, friction force, and acceleration effects. So gravity is due to hydrostatic forces. I think we have explanation. Yeah. The total pressure difference will be gravity term, friction term, and the acceleration term, the inertial term. So if we picture ourselves at the bottom hole, so look up in the tubing, what we will see, we will have an anti-gravitational force of flow, because since everything in the earth is attracted towards center of the earth, towards the core, but whatever fluid is coming in the tubing, it is flowing in an anti-gravity direction. This means the pressure at the bottom hole is so much that it is delivering the fluid from bottom hole till surface. So this gravity term is the maximum component that is having in the total pressure difference, because that is against gravity. Then friction term comes in when we have a curvature in the TPR. I'll show you the TPR also, and even acceleration term due to velocity forces. So this is the actual TPR. So if you see from this region to this region, it is density dominated flow. It means the velocity forces are trying to stabilize in this region. This region is where the flow is unstable because inertial forces are dominant. Inertial forces are dominant in this region. But once they are stabilized, then there is friction domination. It means the anti-gravitational flow is stabilized here. For the outflow system, the higher the pressure at the bottom of the well, the more fluid that can be pushed from the well. Of course, that is what we are discussing till now. So this is a typical TPR relationship. So when we combine IPR and TPR, we will have the nodal part. So whenever, I think there are some production or reservoir engineers in this group as the audience. So whenever you do a pressure survey, we generally take the flowing gradient, okay, for the well. So we have different sensors at the bottom hole. So this will measure the pressure at every point in the tubing. So this will tell us the pressure drop from the bottom hole till the surface. So this, if this constant slope, if it is having maybe 0.3 psi per feet, that is oil gradient. If it is having a slope of 0.08 psi per feet, that is gas gradient. This is oil. If this is having 0.433 psi per feet, that is water gradient. So if you have ever observed the gradient profile, then you can understand this. This is important for our VLP calculations, which I'll tell you in the actual course. So what is gradient? The change in pressure to the change in depth. So this is the combination of the IPR and TPR. If you see, the pressure drops are plotted against flow rate to give IPR and also TPR. So if you can see, if I take this as a base TPR curve, the actual sharp one, that is generally for 3.5 inch tubing. So if you can see, if I'm increasing the tubing size, it means I'm giving more area of the flow. So if I consider this as 3.5 inch tubing, 3.5, and if this is 4.5 inch tubing. So what happens? Simply Q is area times velocity, the actual flow rate in the tubing. If my area is more, my Q will be more. So if you can see, this point of intersection between the IPR and TPR is the operating point. This operating point is what will tell us whether we need to go for nodal analysis or not. If the operating point is sufficient enough for the company to believe that this well doesn't need nodal analysis, it means we can save a lot of money and a lot of time. But if the well can actually deliver this much of flow rate, so operating point is always the maximum flow rate that the well can deliver. If that can deliver this much, but it is delivering only this much, it means we need to optimize this, So optimization will be changing the tubing size or increasing the choke size, whatever. We can understand it everywhere when we actually work on a typical simulation software, which is Prosper, that we actually deal in this course. So IPR and TPR curves can be combined to find the stabilized flow rate. So tubing shoe reaches the perforation depth. Wellbore flowing pressure and tubing intake pressure are considered same depth at the same depth. At a specific rate, when these two pressures are equal, the flow system is in equilibrium and the flow is stable, right? That is at the operating point. So whatever fluid is coming from the reservoir pressure to the bottom hole pressure is actually being carried out from the bottom hole to the tubing to the surface. That is what we are actually should understand. So if the left towards left, what happens is there is increase in PW due to fluid hold up. That is mostly due to inertial effects. But towards the right, increase of PW due to increase in friction, where the friction forces dominate. That is what is important for us. So this is the operating point, which can be the point at which the FBHP of from the IPR is equal to the FBHP of the TPR. The intake pressure is exactly equal to the output pressure from the reservoir, which gives a stable flow rate. So if I go for a sensitivity of tubing sizes for D1, D2, and D3, if you can see D1 is less than D2 is less than D3. The same principle. If I'm increasing diameter, I'm getting more flow. That is the funda. And if I look at three different wellhead pressures, so this is PWH1, WH2, and WH3. What I'm doing is I'm reducing the wellhead pressure. If I'm reducing wellhead pressure, I'll get more flow rate. That is the fundamental. So see, if you can see if I'm increasing wellhead pressure, depending on the optimum point that I have understood, so my flow rate also increases. So this PWH should be the minimum at maximum flow rate, and this PWH should be the maximum at minimum flow rate. So well deliverability. So now we actually entered the nodal analysis concept. So well deliverability is determined by the combination of well inflow performance and well bore flow performance, which is the PPR or the VLP, vertical lift performance. So this study or the work that we are actually should be going ahead with focuses mostly on prediction of achievable fluid production rates from the reservoirs with specified production string characteristics. This is called nodal analysis. It is first actually deliberated by Gilbert in 54. So applications of this can be understanding the estimation of flow rates, selection of tubing size depending on the optimum point, selection of flow line size at surface, selection of wellhead pressure and surface choke configuration. Should we install artificial lift and design it in the future? Estimation of effects of reservoir pressure depletion, and also understand the flow restrictions or the bottlenecks from the reservoir till the facility. So the procedure of optimization includes identifying the components in the system, then select which component should be optimized, then select the node location that will be best emphasizing the effect of change, develop expression for inflow and outflow, calculate delta P versus flow rate for all components from the reservoir till the surface, determine the effect of changing the characteristics of the selected component, then repeat the procedure for each component and also optimize the production system. So when we start, we will select the model options in the simulation software. Then we set up and match the PVT model, which is very important. Then we go for inputting system equipment and IPR relationships. Then we match IPR and VLP, which is very essential in going into the optimization procedure. Then we calculate system sensitivities, and then we get a performance, which is either acceptable or not. If it is yes, it is finished. If it is not, then again review design and again go to system input. So we will be doing sensitivities like this. So this is the complete picture of analysis where we simulate the fluid from the system. It is necessary to break the system into discrete nodes that separate the system elements. As I've told you, bottom hole node is one, wellhead node is one, and choke node is one. So these are several equipment sections. The fluid properties at the elements are eventually evaluated locally. So NA is performed on the principle of pressure continuity, the pressure from reservoir till the bottom hole, from that to wellhead, from that to choke, then to separator. That is, there is only one unique pressure value at a given node, regardless of whether the pressure is evaluated from the performance of upstream equipment or downstream equipment. So if I talk about bottom hole node, upstream equipment is the reservoir and the downstream equipment is the tubing. The performance curve, which is pressure rate relationship of upstream equipment, is called inflow performance IPR, and the downstream should be OPR or the TPR or the VLP. If I talk about bottom hole node, the intersection of the two performance curves defines the operating point, that is operating flow rate and pressure at the specified node. So if I talk about the optimization, before optimization, I'm getting my Q as 97 mmSCFD, but now after optimization, I need to optimize this to bring it towards the bottom. So if you can see, if I do sensitivity of tubing diameter, I'm getting flow rate of 104, which is way better. So I can change my tubing size depending on the study that I have to. So also the actual flow rate will be this 76, 94, and 101 for different uh, node pressures of the surface. Then also for different uh, water cut percentages, if I consider 0% water cut, I'm getting 97 MSCFT. For 40% water cut, I'm getting 80 MSCFT. The point is to choose which water cut sensitivity, because we need to also handle water at surface. That is very important. And also for skin, if I reduce my skin, what is my flow rate? See, for a skin of +1, it is 114. For a skin of +7, it is 84. If you can see, there are two IPR curves, because skin is only a reservoir effect, not the wellbore effect. So skin, if I take the first 0, that is 1, take +7, I'll get a narrower IPR. So substantially my flow rate is also reducing. The optimum part is reducing. So there is a formation damage. I can mitigate this by doing a matrix resizing job or a HF job or whatever, simulation jobs. So after optimization, we are going ahead with choosing a water cut of 5%, which is reliable, and also skin of 1 +1. So we are comparing the pre-optimization, which is how much? If I go back 97, now post is 114 +17 I'm getting. So 114 is the optimum flow rate for this well, which I can do by changing tubing size to 6.8 inch and maintaining valid pressure of 2000 psi, and assuming a water cut of 5%, which is considerably good, so that I can handle this water cut and of skin factor of +1. So results during the production: chosen well with tubing size of 3.95 inch and 4.78 inch causes restriction because of tubing, but the production rate increases at the production with tubing size of 6.18 inch. According to the production potential of the well and reservoir and capacity of surface equipment, valid pressure of 2000 psi for the well is appropriate. If the creation restriction is bottom hole completion or formation damage is reduced, we can go for HF or acidizing job to improve using the workover, and that's the cost also for the company. So they will evaluate everything from their NPV analysis, net present value. Also from formation stability, completion by the method of open hole is appropriate, and there is no need for mechanical integration junction. Let me just share the presentation with you. So this is a study of production automation of an oil well using Prosper. So we will be looking at Prosper in this course, and if type permits, we will also look at PipeSim, but I can't guarantee because both can take time together. If you are willing to attend course for 10 sessions, then we can do it. But if not, so there are time constraints for everyone. So we will only look at one software, which is Prosper. So in this course, the objective is to optimize well performance in order to maximize the production rate. So oil reserves are depleting every day, and the prices are also peaking. Thus, we need to uh, do optimization, which cannot be neglected. So the procedure is to determine which component system can be changed, as I've told in the workflow before. So we select one component which can be optimized, and the thing is we can only optimize one component at a time in Prosper, because Prosper is static software. But in Pipes we can optimize multiple components, which is of Slumberger. But Prosper is from IPM. So we will set the node location that will best emphasize the effect of the change in the selected component. We develop expressions for inflow and outflow. We obtain required data to calculate pressure drop versus rate for all the components. We will also determine the effect of changing the characteristics of the selected component by plotting inflow versus outflow to get the optimum point. And we repeat the procedure for each component that is to be optimized. So Prosper is chosen. So to give you a brief outline about Prosper, Prosper is a well-performance design and optimization software. It is designed to allow the building of reliable and consistent well models with the ability to address each aspect of the wellbore, which is PVT characterization and VLP correlations for the calculation of flow line, tubing pressure loss, and the inflow performance relationship. The very basic benefit of simulation software is to match a correlation with the actual production rate happening in the in our well. So as a workflow, what analysis we do? So we start the model first. We set the options, set up and match PVT model. We input system equipment and IPR, and we choose artificial lift. If yes, we will go for new design and we enter the artificial lift data. If not, we will go to IPR and VLP matching. Then if the VLP is consistent, if it is actually matching the surface production rates, it is okay. If not, again go back to your PVT model, because generally we need to match the PVT. That is most important, because the pressure of reservoir is declining day by day, and that won't honor your initial PVT model. If it is yes, then we can calculate system sensitivities. And now if we should do new design, if it is yes from the artificial lift, we go for lift method selection. Then we perform gas lift design if it is gas lift. If it is not, if it is ESP, we perform pump design. And if it is okay with us, then we go and we enter that after the consistency of VLP is obtained. Then we do system sensitivities. As I've told you, the nodal analysis part comes here. Then we do performance acceptance. If it is okay, then finish it. If it is not, then review the design. So this is the well that is selected in this case study, X3. The field is developed using 5 wells and reached peak production in 1996. Since then, oil production has decreased rapidly due to increase in water content or water cut. So economic limit of this field is 1,500 STP of oil per day per well, which is premised, and that is production at lower rates. That is not economical because there is a lot of cost in operating also. So what depth? The depth is 300 feet from the mean sea. Sorry, the depth of water, the mean sea level is 300 feet from surface. Then the porosity is 22%. Perm is 200 millirc. KU by KS ratio, the vertical to horizontal permeability is 0.1. Top sand is 6,400 feet TVDSS. The reservoir top. Then OWC is 6,500 feet TVDSS. So the oil rim column is 100 feet. The PI is 33000 PSI, and the recent PI is 2800 from the static bottom hole pressure survey. So the PV data is given here. So temperature is 150 degree Fahrenheit. Oil API gravity is 40, which is very light or volatile. The relative density of gas is 0.8, the gas gravity. The GOR is 550 SCF for STP. PB is 2030. So the current PR is 2800. It is single phase. It is a what do we say? It is not saturated. Okay, it is a single phase flow. So BO is 1.27, viscosity of oil is 0.66, BG is 0.0046 at initial pressure, viscosity of gas is 1.023, and Z factor is 0.73, and salinity of water 2 lakh ppm. It is more because it is producing water, and viscosity is 0.67. So the reservoir is unsaturated because P is more than PB. So from pressure survey, we have got these pressure profiles or the pressure values. So from 650 feet it is done to 6490 feet up to the reservoir top, which is 6400 feet. So it could be maybe across the perforations. The pressure at the perforation is 2266 psi. The static pressure. So you can see the drop. So what is PB here? PB is what it is, 2030 psi. So when can you expect gas to come in? At the very first pressure point. So since the 5587 is the depth at which pressure is 1920, we can expect gas coming out here in between these depths. So it is very critical to understand. So well data, current production rate is 4730 STP per D. Water cut is 30%. It is more. Wellhead flowing temperature is 65 degree Fahrenheit. The Christmas tree pressure, the wellhead pressure is 445 for PSIA. You can see at 650 feet it is 525, but at wellhead it is 445, which could be 300 feet, the water depth. Skin is 2.92, it is even more, 3. The PI is 12.3, it's also good. Then the damage zone radius or permeability is 40. The thickness is 12. Crush zone skin is 0.1 at the surface from the, I think it's from core analysis. Then damage radius is 4000 feet. So we have equipment data also that will be inputted in the Prosper model. So the objective is to develop a well performance model using Prosper. We simulate base case forecast under various operating conditions, and we evaluate various development options to optimize oil production and the results. So this is the data entry in Prosper, which can be, you can go through from the previous slides. Everything is written: tubing flow, no emulsion, producer. So this is the well completion diagram that Prosper generates for us when we enter the well completion, the well equipment data. this is the initial IPR for an AO. You can say the AOF, it is 25,000 ST per day at zero bottom, at zero surface pressure, when it is open to atmosphere. So this is the matching that we achieved. So measured is 4730, but calculated is 4704. It is very close. Difference is minus 0.5%. So that is the IM. To go ahead with the model. So we can also go and do the matching from PVT. So the base case forecast under various operating conditions is, since the PVT and IPR and VLP were matched to measure data, it was possible to move on. So water cut we have chosen is 30, 35, 40, and 45, and PR 2500, 6, 7, and 8 gauge pressure. So base case is this 45% water cut and 4703 SG per day. So for these 4 water cuts, look at the oil rates. So for water cut of 30% and the pressure of 2800, we got 4703, which is the base case. But for water cut of 45% and the reservoir pressure of 2500, it is 0. We are not getting anything. So for a pressure of 2600 psig and a water cut of 30%, it is 3120. It is decreasing. Since the PR is decreasing, it is decreasing. Also, since the water cut is increasing, it is decreasing. You can see 4703, 3818, 2993, and 2232. Let's look at that from plots. So we are in this case study, they have also evaluated various development options to optimize oil production. Since it is run on the current reservoir conditions, for decreasing wellhead pressure was performed, because wellhead is in our hands, we can decrease it anytime based on choke. WHP is registered using choke in an oil well. Reduction in wellhead pressure causes the drawdown to increase, which in turn increases the oil production, of course. So for different wellhead pressures, you can see the increase in oil rates. For a WHP of 100 psig, the oil rate is 6153. It is very more. So that sensitivity can also be done. But the point is, you cannot even exceed a critical drawdown, because that can also initiate sand production. So we can also lower the crispity pressure, which is generally the wellhead pressure, for an economic water cut of 70% to give a production rate of 6153 STV per day at 45% water cut, if you can see here. So from changing tubing size, we can also see the effect of increasing flow rate. So if you see if the tubing size is increasing, the oil rate should actually increase. So what is happening here? I think since they are continuing everything, they're combining everything together. Since tubing size is increasing, the oil rate is decreasing here. That should not happen technically. So the effect of increasing tubing size is to give a higher node pressure for a given flow rate, because the pressure drop in tubing is decreased. If tubing is too small, then the reservoir may be capable of producing a large amount of fluid. Too much pressure drop occurs in the tubing. So what they're doing is they're combining that effect before with a high water cut and a low reservoir pressure with the actual tubing size, which is actually not appealing to the model. Since they're increasing tubing size ID, the oil rate is decreasing here. That is what is happening. So this sensitivity is generally not done in the actual model, or it cannot be taken forward in the field for optimization. So they have chosen gas lift method to based on current conditions and engineering assumptions. Purpose of injecting gas into the tubing is to decrease the density of flowing gas liquid mixture, because as we have seen, the separation is happening at the bottom hole itself, and therefore decrease the required flowing FBHP. As the gas rate is increased, the fluid velocity and therefore the friction loss also increase. So for gas injection of 2 MSCFT, we can understand at water cut of 45%, we are getting 6908 ST per day. But for a gas injection of 4 MSCFT, it is 7111. It is beneficial actually. So economic oil rate with optimized gas lift is for 80% water cut, they are getting 6900 ST per day as the optimum production rate at 40% water cut. So the results can be, we can lower the crispity pressure or the wellhead pressure to 100 psi. If the water cut can be up to 70%, if we can handle surface water. The next possible option is to change the tubing size. However, changing tubing size is not recommended, because you can see it is not giving fruitful increment in oil production rates. It is decreasing actually. The gas lift method is more economically beneficial, and as it produces up to an economic water cut of 80% with gas injection rate of 2 to 4 mm sand cubic feet per day, producing oil rates of 1800 to 2000 ST per day. So this is the result that they have generated. So let me just go back to the previous presentation. So the case study is now complete. So we will be doing 3 case studies in the actual course. So we have 3 case studies, the real case studies. So we'll be looking at those 3 case studies, and actually you'll be working with me in Prosper. So why is this course suitable to you? That is what we have to understand. So if you're an entry-level engineer, it is very beneficial to you because you learn everything from scratch. As I'll be teaching you from the very starting of the production system, how it is developed and how we should carry or travel with it. For a mid-level professional, if you are a reservoir engineer or completions engineer or a production or drilling engineer, it is beneficial because you'll be learning a computational software to optimize production. So this can help you to be an expert in production automation as a field professional. So the actual course plan will be shared to you in due course of time, because we are still working on the course plan depending on your interest. If you have any suggestions what to include and what not, we will work on that direction and we'll be sharing the course plan by tomorrow. So yeah, thank you for your time. If you have any doubts, just let me know in the chat box, or even you can unmute yourself and ask. Anyone? Any questions? Like suggestions, what to include and what not to include, you can tell us now. We'll be more than happy. Any doubts? Anyone?
Sir, thanks for the session, sir. May I know the simulation software name, sir?
It is Prosper, IPM PROSPER, a static well modeling software. And if time permits, we'll also look at SLB's PipeSim, PIPESIM, a dynamic simulation tool. Yeah.
Sir, is it available in online, sir? In Google?
You can actually download the crack version, but I don't recommend it because you'll be caught easily. But I have the license, so I'll be taking you through that. If you want assistance, I'll also share you the license file with you in future.
Okay,
if you join the course.
Sir,
yeah.
If we refer, any tutorial is available, sir, in YouTube or?
Yeah, they'll be available, but yeah, they won't teach at your level. You actually need from scratch, right? So if you can see tutorial to understand the procedure or workflow, but if you want to run, you need to start from scratch.
Okay, sir. Thank you so much, sir.
Welcome. Okay, one thing in chat. Okay. Anything else?
Sir, if you don't mind, kindly share the PPT presentation, sir, if possible.
Yeah, sure. It will be shared with you. It will also be uploaded in the. I think it will be also uploaded in the YouTube. I hope. Oh. Yeah, we will share it with you.
Okay, sir. Thank you, sir.
Yes. Okay, if no one has anything, we can end it here. If you have anything else, you can discuss in the group also. We will be answering your queries depending on how to fine tune this course for your requirements. That is how we actually do it, because this is not just me teaching you, it is we learning. I teach you, you also tell me in return. That is a two-way communication. That is what I always expect from audience. So yeah, you can just let us know what you actually want in the course. We will include that. Okay, thank you very much. All the best. We will look for the update in the future.